Hello and welcome to Algebra Lesson 6-1. We are moving on to Chapter 6. We're going to be moving into Lesson 1 of that chapter. Today we're going to be solving systems by graphing. There are many different ways to solve systems. Today we're going to go over how to solve them by graphing. Okay, let's go ahead and get started, as we always do with our anticipatory set. Now, one thing I've always been impressed with is NASA. Is space travel, space exploration. And one of the things that's so impressive about it is just how much math and calculations need to go into it. So let's say this is the planet right here, right? And let's say we have the International Space Station floating in space like this, out here like this. All right. And someone is trying to dock with the International Space Station. What they need to do, because obviously, since the International Space Station is around Earth, it is orbiting. So it is orbiting the planet around and around and around. So if we're going to send a rocket up to the space station, all right, so that's our little rocket. If they're going to send one up, there we go, there's a big old flame behind it. They need to calculate where these two things will connect. Because if you launch at the wrong moment, if you say, okay, we're going to launch, and you launch here, you're looking at it, and you say, oh, I'm going to go get it, and you're flying this way, this is going to orbit, and by the time you get there, it's going to be all the way over there. There's no way to find it. So there needs to be math, knowing, okay, the speed it's going, the orbit it has, as it comes around, okay, maybe right here we've projected its path, it's going to be right here. So we're going to launch, and with the way the Earth is turning, if we launch at this moment, we will meet right here at this exact moment. Always found that impressive that people can do that. And that's partially what we're going to be looking at today. Obviously, nowhere near what NASA does, but it's similar in that we need to find a place where it's going to work out for both the space station and the rocket. So let's go ahead and get into our standard for today. And our standard is going to be A.REI.6. It's going to be algebra. And the standard states that we need to solve systems of linear equations exactly and approximately which of course means with graphs, because obviously that's what we're talking about. With graphs, focusing on pairs of linear equations in two variables. Okay, so that's our standard we're going to be working with today. We are going to solve systems of linear equations exactly and approximately, focusing on pairs of linear equations in two variables. Remember, two variables means we're going to have an x and we're going to have a y. Okay, so we're just a bit, there we go. Okay, so let's go ahead and get into our input. Now, this is a new section we're moving into, which, for that reason, we're going to have quite a few languages of discipline to go over. Okay, so we have several terms to go over today. So I'm going to go ahead and start with our first one, which is system of linear equations. System of linear equations, which is important because right here it says systems of linear equations. So, what is a system of linear equations? Well, a system of linear equations is two or more linear equations for the same plane. So on the same plane, two linear equations. Now there could be 3, 4, 5, 6, 7. We're only going to deal with 2 today. But anytime there are more than one linear equations on the same plane, that's called a system of linear equations. Next, we have a solution of a system of linear equations. Very long term. But a solution of a system of linear equations is any ordered pair that makes all of the equations in the system true. Any ordered pair that makes all of the equations in the system true. Not just one, but all. Okay, the next one is consistent. Obviously, not just the word consistent. In terms of what we're talking about today with math, consistent is a system of equations that has at least one solution. So if there is a system and there is at least one solution, then that is consistent. Now the next two terms are going to be sort of part of consistent. The first one we're going to do is independent. So I'm going to say this is part of this one, and the next one's going to be part of the next one too. Independent means a consistent system that has exactly one solution. So independent is a consistent system that has exactly one solution. So consistent means there's at least one, but independent means exactly one. The next one is dependent. And dependent, you can probably guess, but it's a consistent system that has infinitely many solutions. So independent means there's exactly one. Dependent means there's an infinite number of solutions. And our last term today is going to be inconsistent. You may be able to guess what inconsistent would be as well, but I'll go ahead and write it. A system of equations with no solutions. Okay, so that covers about all of it, right? We have what a system of linear equations is, what a solution is, and then whether it's consistent. If it is consistent, it can either be independent or dependent. If it's not consistent, that means it is inconsistent and has no solutions. Okay, before we move on and get some input modeling down, there's going to be one thing I want us to note. Now, as you'll see as we go through chapter 6, is that there's many ways. So, systems of equations can be solved in many ways. One way is to use graphs with each equation. And that's what we're going to go ahead and go over. Okay, so you'll see a lot of different ways for us to find this. However, today we're going to go ahead and work on graphing. Okay, I'm going to go ahead and grab a different piece of paper. And we're going to go ahead and start our input and modeling. Okay. So we're going to do a few examples. In these examples, you're going to see things you remember because we have graphed before, we have used equations before, but now we're putting these together. So the first thing we're going to do is we're going to solve a system of equations by graphing. So solving a system of equations by graphing. Solving a system of equations by graphing. Okay, so our first problem is going to be, what is the solution of the system? Use a graph, obviously. Okay, here are our two linear equations. First one we're going to have is y equals x plus 2. Second one is going to be y equals 3x minus 2. Okay, so our system of equations are these two. They're on the same plane, and we're going to go ahead and use graphing to find if there are any solutions. So I'm going to go ahead and draw out a graph. Here's -2. Here is 2, 4. I'll move that up a little bit. Here is -2. Here is 2, 4. Okay. Now, if we know that a line, the line of this graph is the solution of this graph, and a line of this graph is the solution of this graph, what we're going to be looking for is the intersection. The intersection is the solution. So before we start writing these out, I'm going to use two different colors for each of these. This one's going to be purple for me, and this one's going to be this light green for me. Okay, so let's start with the first one. Y equals x plus 2. Now we know some information about this. We know how to graph. So the slope here is going to be, well, x has a 1 in front of it, so the slope is 1. The y-intercept is positive 2. So I can go ahead and graph the solution of this equation, which I will right now by finding the y-intercept. That's 2. The slope is 1, meaning I'll go up 1 over 1, up 1 over 1, up 1 over 1, over 1, or down 1 over 1, down over, and then I just go ahead and connect those, and I have my solution. So that's my solution for my first equation. Now we need to see where these equations intersect, because that means they'll be the same. So my second one is y equals 3x minus 2. The slope in this case is going to be 3, so 3 over 1. The y-intercept is going to be negative 2. So I'm going to go over my graph a point at negative 2. I know that I'm going to be my slope of 3, which is up 3, 1, 2, 3 over 1. Up 1, 2, 3 over 1. Oh, I see an overlap. I'm going to go ahead and connect these lines. Okay, so I have my two solutions of the individual equations, but I also see that right here I have an intersection. So what is this intersection? The intersection is two, well, actually, I figured it out, but I'll look at it. From the origin, 1, 2, 1, 2, 3, 4. 2, 4 is our intersection. Now, graphs, sometimes I don't draw them exactly correctly, so maybe I'm a little wrong. So let's go ahead and check by plugging this ordered pair into both of our equations. Let's see if we're right. So I'm going to go ahead and check. First one, y equals x plus 2. Okay, here's the x, here's the y. The y is 4 equals 2 plus 2. 4 equals 4. Okay, one of my equations is absolutely correct. Let me check the next one. Y equals 3x minus 2. My y value is 4 equals 3 times 2 minus 2. 4 equals 3 times 2 is 6 minus 2. 4 equals 4. I've checked my second one. That is the solution. So the solution of the system is 2, 4. So just like in our anticipatory set, the thing that's always impressed me about space travel is that you have to deal with both of the paths, one of wherever you're going, one of the ship you're flying, and you have to find out exactly when they're going to meet. Well, similar to what we're doing here, we are finding this path, finding that path, and discovering what the point of intersection is. Okay, I'm going to move on to our second one. And our second bit is going to be writing a system of equations. Writing a system of equations. So we solved a system, but how do we get to this point? Why is this important to know? How do we use it? So here is our problem. Scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth rate of each is shown below. After how many months do the alligators weigh the same amount? Okay, so we have our problem. Now we need to go ahead and solve it. So I'm going to go ahead and list the initial weight and growth rate of both alligators below here. Okay, so alligator 1, I'm going to use 2 different colors again, and because the Broncos are cool, I'm going to go ahead and use these 2 colors. They're old colors. Alligator 1. Alligator 1, its initial weight is 4 pounds. Its rate of growth was 1.5 pounds per month. Alligator number 2. Its initial weight, 6 pounds. Its rate of growth was 1 pound per month. Okay, so we have our information on both alligators. Now, the first thing we want to do is we want to talk out what our equation would look like. So, in words, what would we do? In words, the way we would say it to find out what the alligator size is right now would be alligator weight is the initial weight because you need to know how much it initially weighed, plus the growth rate. Should have actually said plus because we're doing words. The growth rate times, and what does the growth rate rely on? The growth rate relies on the time. So in words, we would say the alligator weight is the initial weight plus the growth rate times the time. Now, for each of our alligators, we're going to fill in what we know. Okay, so let's start with alligator 1. Alligator 1, do we know what it weighs right now? No, we don't. Okay, so alligator weight is going to be our variable. W equals, because is always is equals, the initial weight. We do know the initial weight, which was 4 pounds. 4 plus, we know the plus sign, growth rate 1.5 times the time. Do we know the time? How many months? No, we don't. So that's going to have to be our variable. So our equation is going to look like W equals 4 plus 1.5t. Now let's go ahead and go to alligator 2. We know the same information for alligator 2, which means our alligator weight is going to be our variable as well as the time. So W equals, do we know the initial weight? Yes, we do. 6 plus the growth rate, which is 1 pound, 1 times the time. We do not know. So our equation is going to say W equals 6 plus T, because we don't need to write that 1. Okay, I'm running out of space here, so I'm going to go ahead and move to a different piece of paper. And we're going to continue with what we're talking about right here. Okay. What I'm going to need to draw out, is a graph. They said that the weight starts at 4 and 6, so I'm going to need to go pretty high on the weight. And the time means how many months. So on one side, I'm going to need the weight. My x is going to be time. The time is by month, so I'm just going to label these 1, 2, 3, 4, 5, 6, 7, blah, 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 blah. The weight, however, is starting at 4 and starting at 6. So it needs to go up a little higher. So I'm going to count by, we'll do 2s. 2, 4, 6, 8, 10, 12, and on and on and on. Okay, so we have our weight and we have our time. Once again, I'll write these out over here so we can see them. We have alligator 1, which is W equals 4 plus 1.5 T. And we have alligator 2, which is W equals 6 plus T. Okay, so what is it that we know for both of these? Well, for alligator 1, we know the slope. The slope is going to be 1.5, which we kind of need as a fraction, which is 3 over 2. We also know the y-intercept, which is 4. Down here, we also know the slope. The slope is 1. The y-intercept is 6. So we know all that information. Now let's go draw our lines. Well, alligator 1, the y-intercept is going to be 4. So I'm going to put my mark right there. And then the slope is going to be 3 over 2. That means up 3 over 2. So remember, I'm counting by 2 here, so I need 1, 2, 3 over 2. 1, 2. 1, 2, 3 over 2. 1, 2, 3 over 2. I have my growth rate for my alligator 1. And on and on and on. Now I need my growth rate on my line for alligator 2. The y-intercept is actually going to be 6. The slope is 1. Remember, I'm counting by 2's here. So 7 and over 1, over 1, over 1, over 1, over 1. All right, I'm seeing my pattern there. And it looks to me that this is going to be our intersection. So I need to go ahead and find what that intersection is. Whoops. What is this intersection? Well, the x value is going to be 4. The y value is going to be 10. So this is 4, 10. But I want to check. And to check, I need to check both equations. So let's start with alligator 1. So we have W equals 4 plus 1.5t. We substitute our x and our y values, which y in this case is going to be W. 10 equals 4 plus 1.5 times t, which is our x value, 4. This will be 10 equals 4 plus 6. 10 equals 10. We've checked one of them. Let's do the next one. W equals 6 plus t. We plug in our values. 10 equals 6 plus 4. 10 equals 10. Check. I have both of them right. That is our answer for number 2. We wrote a system of equations. We checked to make sure that they were correct, and we made sure that they were. Okay, last modeling question. And this one is, what if we get to the case where we have infinitely many solutions or no solutions? What if we get into this situation? Let's take a look at a chance on each of them. Okay, first of all, we're going to have a little bit of a note here. Sometimes a system will have more than one solution. Sometimes it will have none. See the examples below. Okay. On one side, I'm going to go ahead and show you a graph of an infinitely many solutions. So on this side, we have infinite. So let's draw a little graph here. Okay, and what if we have a situation where these are our two equations? Y equals 1/2, oops, sorry about that, there you go. Y equals 1/2 x plus 1. And the other one is 2y minus x equals 2. Now, both of them are not in y-intercept form. So let's go ahead and convert this one to y-intercept form. We add x to this. We add x to this. We now have 2y equals 2 plus x. We then divide by 2, and we divide by 2. Y equals 2 over 2 is 1 plus 1x. So it's going to be 1/2 x. As you can see, even though they are flipped around, this is the same equation. So let's go ahead and graph this one. Our y-intercept is going to be 1, and our slope is up 1 over 2. Up 1 over 2. Now if we graph this one, the x-intercept or the y-intercept is 1, and the slope is up 1 over 2. And you can see it's the exact same equation. So every part of this line is a solution. Meaning, since this line goes on to infinity in both directions, that there's an infinite amount of solutions. So that's how you see that there's an infinite amount of solutions. Now, over on the other side, what if we had one that had no solutions. So again, I'm going to go ahead and put a little graph. And our two equations are going to be y equals 2x plus 2 and y equals 2x minus 1. As you can see, the slope is going to be the same on both, but the y-intercept is different. So let's see if that makes a difference. This one, our y-intercept is 2, and our slope is up 2 over 1. Up 2 over 1. So for infinity in that direction, infinity in that direction. Let's look at our next one. -1, and we have the same slope, up 2 over 1. Up 2 over 1. Up 2 over 1. So you can see these are going to be parallel lines and will never touch, meaning there are no solutions. That is the end of our work for today. Your guided practice is going to be our PPSE, but this time we're going to be doing number 12 through 26 even. I want to give even a shot too. And our independent practice is going to be lesson 6-1 quiz. And that's assigned on your Pearson Success Net. That's everything. Enjoy, and I'll see you next time.